Hello everyone. In this video, I'm going to be talking about some of the addition reactions that we talked about in class, and we'll start with hydrohalogenation. And just like the name implies, we're adding a hydrogen and a halogen across a carbon-carbon double bond. Remember when we talked about elimination, we were eliminating two groups across a carbon-carbon double bond, right? And in addition reactions, we're adding two groups across a carbon-carbon double bond. So here's cyclohexene, but I'm going to make it into a methyl cyclohexene, right? So suppose you start off with a methyl cyclohexene and you add hydrogen bromide, right, to it, and that's our reagent. To hydrohalogenation, we're adding two groups, a hydrogen and a halogen, and we know that pi bonds can act as nucleophiles, right? So they'll attack or they'll form a bond to the less nucleophilic or the more electrophilic atom of the two, right? Meanwhile, the hydrogen and the bromine have two options, either adding on this carbon or on that carbon. So what we need to keep in mind is the following. Are both carbons exactly the same in terms of what is substituted to it? If we take a look at this carbon of the carbon-carbon double bond, it has two groups attached to it. If we take a look at this carbon of that carbon-carbon double bond, then it only has one group attached to it. All right, so this end is more substituted. So in hydrohalogenation, the bromine or the halogen adds to the more substituted position of the carbon-carbon double bond, and we call that a Markovnikov addition, right? But I'll say a Markovnikov addition of the halogen, right? It's the halogen that is being added to the more substituted position of the carbon-carbon double bond. In hydrohalogenation, the reagent is really HX, where X is really either bromine or chlorine, right? Okay, that's our reagents. Okay, so now let's try the mechanism. Okay, so we have hydrogen bromide. We know that the pi bond is acting as a nucleophile, and it will attack the more electrophilic of the atom. Hydrogen is less electronegative than bromine, so the pi bond will attack the hydrogen. And if a bond is formed, remember a bond has to be broken. Okay, so we still have the methyl group. Now we just added a hydrogen, right? Will the hydrogen add to the less substituted position or the more substituted position? If you take a second and think about it, those two electrons are going in to form a bond to the hydrogen, right? So a carbocation will form either on this end or on this end, right? This is a tertiary carbocation, this is a secondary carbocation. This carbocation is more stable, so we form the more stable carbocation. That's why later the halogen adds to the more substituted position. All right, so we have the bromine, which now carries a negative charge because of those two electrons. The bromine can act as a nucleophile. It can attack the carbon, right? And really, we're getting to the final answer by doing so. It goes through a carbocation, so it's much like an SN1. In fact, this second step is much like an SN1 mechanism. So are we getting the bromine on a dash or a wedge? Right. We get both enantiomers, right? This could be on a dash, or it could be on a wedge, right? So you end up forming both options. The nucleophile, in this case, the bromine being on a dash or a wedge, right? So you could form two enantiomers in this case. What if we wanted an anti-Markovnikov addition? What if we wanted the bromine to add to the less substituted position of that carbon-carbon double bond? Then we use slightly different reagents or reaction conditions. We still have hydrogen bromide, but what we do is we add peroxide, right? it goes through a different mechanism, but the result is an anti-Markovnikov addition, right? You go through a radical mechanism, anti-Markovnikov addition, where the halogen now, in the presence of a peroxide, the simplest is hydrogen peroxide, the halogen adds to the less substituted position of the carbon-carbon double bond, and we call that an anti-Markovnikov addition. So there's hydrohalogenation, could be a Markovnikov addition, or an anti-Markovnikov addition in the presence of peroxide, right? You're adding two groups across a carbon-carbon bond, a hydrogen and a halogen. And just remember, we don't see halogens, hydrogens attached to carbon atoms. Okay, so now let's do a different one. All right, this takes a long time to clean, but we're going to get this done. Okay, so now we're going to consider halogenation reactions. Okay, what if you wanted to add two halogens across a carbon-carbon bond? Halogenation. So suppose we start with cyclohexene, and we will just make it into a methyl cyclohexene, right? And we are adding Br2, right? So halogenations, we're adding two halogens across a carbon-carbon bond. We'll get a methyl on a dash, bromine on a wedge, bromine on a dash, right? So if you notice, both bromines, one is on a dash and one is on a wedge. They're trans, right? Both bromines are trans to one another. And what we call that an anti-addition, right? Does it matter? Is it a Markovnikov or an anti-Markovnikov? Well, they're both bromines, right? So they're both exactly the same, so we can't really say Markovnikov versus anti-Markovnikov, but it's an anti-addition. Both bromines are added or trans to one another. And if you recall, ring opening of an epoxide, you end up forming the two substituents across that carbon-carbon bond are anti to one another. All right, so let's try and draw out the mechanism for that one. We have bromine and bromine. Well, typically the pi bond will attack the atom that is less electronegative, right? The more electrophilic atom of the two, but in both cases it's bromine. So what exactly happens? Yeah, the pi bond will still attack one of the two bromines, right? This bromine-bromine bond will be cleaved, but in lieu of forming a carbocation, similar to the example we just did with hydrohalogenation, the bromine has three lone pairs of electron, can act as a nucleophile. It will instead right away attack that carbon that ends up being a carbocation. Now, which one is a more stable carbocation? This one, right? This is the more substituted end, the one that would have formed a more stable carbocation. So the bromine will go in and attack that particular carbon. And what we end up getting, or the result, is all right, or actually I'll just make it big. The result is what we call a bromonium ion bridged intermediate, right? A bromonium ion bridged intermediate, much like an epoxide, right? Well, then we have the other bromine right now, and that bromine will act as a nucleophile. It will attack the less substituted end of that bromonium ion bridged intermediate. So the bromine comes in, attacks, this carbon-bromine bond is cleaved. Those 2 electrons go to bromine. It's really like you erased this. Right, that's all it is. All right. And then we end up getting the final product. Those are much like the epoxide, both on dashes and both are on wedges. So when you end up opening it up, one ends up being the opposite of the other, right? So as long as you draw them anti or trans to one another, you're good. All right, so that's an example of halogenation reaction. And now we'll do one more, known as halohydrin formation, right? Where we're adding a halogen and a hydroxide across a carbon-carbon bond. All right, so the very first step of it is exactly the same as what we just did. Okay. The second step is slightly different. All right, so I'm going to keep the first step the same. The final product is slightly different in that it's a halohydrin. So what we're adding is a halogen and a water, right? Those are our 2 reagents, a halogen and a water. And the product is still an anti-addition, bromine and water, and a hydroxide, but the hydroxide adds to the more substituted addition. So it's an anti-addition, and it is also a Markovnikov addition of the hydroxide, right? Markovnikov addition of the hydroxide. The hydroxide adds to the more substituted position of that carbon-carbon double bond, right? So we have the hydride and we have the bromine, right? Remember, if you add a base to a halohydrin, you can form an epoxide, right? Okay, meanwhile, so the very first step is bromine. The pi bond acting as a nucleophile attacking one of the bromines. The bromine has a high electron density. It'll form a bromonium ion bridged intermediate, but now instead of the other bromine attacking that bromonium ion bridged intermediate, water will, right? So you have water, but it's a Markovnikov addition of a hydroxide, and water is a weaker nucleophile. It will attack the more substituted position of that bromonium ion bridged intermediate. So water comes in, attacks, this bond is cleaved. So now we still have a bond to the bromine. We still have our methyl group, but now we have a new bond to water. You still have the 2 hydrogens attached to it, right? And it's positively charged. And what can happen is either water or bromine. Bromine comes in, deprotonates, those 2 electrons go to the oxygen, and we end up getting our final product. And to just keep it the same, this is a dash, and this is a wedge, right? Which in this case really means that this was the dash, right? Because this is much like an SN2, right? If you think about it, this is much like an SN2. It's happening at the same time. So there's the inversion of configuration. All right. Hope that was helpful. See you next time.